Let's have a small review of what we've learned about probability. We will be going over experimental probability, sample spaces, making predictions, and figuring out how to use probability in these word problems, how to solve and understand these problems. So let's look. Number one, Jolene is playing basketball. She scores 11 out of 15 baskets she shoots. What is the experimental probability that Jolene will get a basket on the next shot? So we have to determine what are her chances of getting her next shot. And how do we get it? Well, we have to know what's the probability of her getting shots in before. And what do we see? 11 out of 15. So before she shot 11 out of 15. So that's going to be our fraction, our probability of her getting the next shot in. So our experimental probability will be 11 out of 15. Because out of 15 past shots, she got 11 in. If we were to turn it into a percent, it would be roughly 73.3%. Okay, so this is the experimental probability. When she shoots her next shot, she has a 73.3% chance of getting in. What is the experimental probability that Jolene will not get a basket in her next shot? Okay, so we know that 11 out of 15 she does make it in. So how many shots does she not get it in? By looking at this. Well, we know she has total 15 total shots, and 11, let's say, are scores. She got in. How much did she not score or get in? Remember, if my 15 is my total, what's my missing part? If you remember a long time ago, you probably were taught part whole, or learning that to find the complement or the other part, you have to subtract. So 15 minus 11 equals 4. So 4 misses. And that makes sense. Out of 15 shots, she scores 11, misses 4. 11 plus 4 is 15. So we know she will not get it in 4 out of 15 times in the past. So this is her experimental probability of missing. And if we turn that into a fraction, 4 divided by 15, we can move our decimal place twice to make this 26.66666 or times 100, and we still get the same thing, 26.6. If you see, if we add this up, this doesn't get exactly 100%, clearly, not 3 plus 6 is 9, so it will be 99.9, but it keeps on repeating, so we're just rounding it, okay? Maybe if I turn this into a 7, that would be better. So we went over experimental probability, okay? What are her chances of getting in or missing? Realize it as a fraction or as a percentage. Joanne spins the spinner on the right at the same time. She spins this and this. What are the possible outcomes? How many outcomes are in the sample space? So we have two different events going on. We're spinning this letter spinner and number spinner. So I'm going to put L for letter and N for number. So what are the total possible outcomes? Well, how many outcomes are here? got A, B, C, or D. So there's only 4 choices. How about this one? 1, 2, 3. There's only 3 choices. So how do we find the total sample space? The total possibilities. Remember, we multiply. We take one event, multiply it by the other event, by the amount of choices. And if I were to write it all out, it would be A1, A2, A3, B1, B2, B3, C1, C2, C3, D1, D2, and D3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are my total choices that we got. We did the math here. We got 12 as well. So either way works. You could count them all out, or you can do the multiplication. For breakfast, Armando has a choice of pancakes, eggs, or cereal, and a choice of milk, hot cocoa, or juice. What are all the possible choices of breakfast he can have? How many outcomes are in the sample space? So again, we have 2 events going on. He has to choose a type of breakfast. Well, let's see, main meal, the main breakfast meal. So I'll just put M. And milk, hot cocoa, or juice, that looks like a drink. So we have our meal, and we have our drink. How many choices does he have for a meal? Pancakes, eggs, or cereal? That's 3. How many choices does he have for a drink? Milk, hot cocoa, juice? 3. And just like before, we're trying to figure out all the combinations. So we multiply, and we will get 9 different combinations. I don't have to write it out, but you would know it's pancake milk, pancake hot cocoa, pancake juice, etc., etc. Okay? Those are all the total outcomes for this combination. All right. Randomly choosing a red card in a game that has 10 red, 10 blue, 10 green, 10 yellow, and 10 orange. So if you could imagine a bin of cards, and he has to choose red, blue, yellow, or orange, or green. It's a little messy here, but it's okay. What are my chances of getting a red card? Okay? So again, for this, we have to create our fraction. What is my possibility over my total? Well, how many total cards are there? We have 10 red, so 10. 10 blue, so that's 20. 30, 40, 50. We add up all the choices together, and we would get a total of 50 different cards. Now, we're asking to choose for a red card. How many red cards are there in the total of 50 cards? 10 red. So our fraction would be 10 out of 50, because there are 10 red cards out of the total 50, not 50 colored cards. Okay? And we can turn this into a decimal by dividing 10 divided by 50. We would get 0.2. And if I want to turn that into a percentage, I can multiply by 100, or I can move this 2 times over to make 20%. Ooh, tossing 2 fair coins and having both land tails up? It's a little tougher. I don't see any numbers, but we have to realize that coins have how many sides? Well, they have two sides, right? So let's do coin 1, coin 2. There's two sides to this coin and two sides to this coin. So we know there's a total possible 4 outcomes. And what are they? Heads, 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 tails, tails, heads, and tails, tails. What are my chances of having both land tails up? If you look at this, how many squares are there? So just like before, what's my probability over my total? My total is 4 because there's 4 different outcomes. We have 2 sides to this coin, 2 sides to this coin, for a total of 4 sides possible. And what's my probability of getting both tails up? Well, there's only one combination of tails on both coins. So my probability is 1/4. If you divide it, you get 0.25. I can move my decimal place 2 points over to get 25%. Remember, 2 fair coins. So we have 2 coins, coin 1, coin 2. There are 2 sides to each coin for a total of 4 possible combinations. And there's only one combination that has tails, tails. That's where this 1 comes from. Now we're going to use our experimental probability to predict what are the possible outcomes. So a baseball player reaches base 35% of the time. How many times can he expect to reach the base in 850 at bats, or when he gets to hit the ball? So, if you remember this one, we do our probability times the number of trials, or the total amount of tries, or total outcomes. So what's our probability? Well, lucky us, we know it's 35%. And how many times is he going to be at bat? 850. Now, unfortunately, I can't just do 35 times 850. That doesn't make sense. If he goes at bat for 850 times, he's going to hit it 29,000 times? No, that doesn't make sense. How can you be on base more than hitting the ball? So remember, we have to turn our percent into a decimal number. So we take our decimal, move a 2 to the left, so we get 0.35 times 850. 0.35 times 850. And roughly, he would get to base 297.5 times. Remember, we take our probability, the percentage or the fraction, and we multiply it by the total tries or total outcomes. Frederica can make 65% of her shots from the free throw line. If she shoots 75 times, how many shots can she expect to go in? So, again, what's my probability? And I'm going to multiply it by my total. What's my probability? 65%. How many times is she going to shoot? 75 times. Turn this into a decimal number. Move it 2 places to the left. Times 75. 0.65 times 75. 48.75. So roughly, out of 75 times she shoots, she'll get in 48.75 times. Okay, so remember, this is just a small review of what we learned before about something being likely, the event, total outcomes. This is the first couple of problems. Our probability, number of times over the total. Same over here. Sample space. What do? We multiply the different outcomes. Let me see where those notes are. The fundamental counting principle right here. So we multiply the numbers of outcomes in each separate experiment. For this one, I think it's tossing quarters. This one is rolling dice. And using our prediction tool by multiplying the probability by the total outcomes. If you have any questions, please let me know. If anything is confusing, rewatch this video or look back to the previous videos to check up on how to maneuver through the topic.